Hello everyone, welcome to today's class. This is Teacher Simon taking you through A-Level Mathematics Papers 9704/45 for May, June 2025. And this is Part 2, Mechanics. Question 5, a car of mass 1,500 kilograms is traveling along a straight horizontal road. Part A, it is given that there is a constant resistance to motion. The engine of the car is working at 24 kilowatts while the car is traveling at a constant speed of 32 meters per second. The power is now increased to 28 kilowatts. Find the acceleration of the car at the instant it is traveling at a speed of 36 meters per second. Now, I'm having this car here on the horizontal road. All right? This car here has gotten a driving force, and then it has a resistance force. Let's say it is R. Now, they said that the car is traveling at a constant speed at first. So you should know that for constant speed, acceleration is always equal to 0. Now, power is equal to FV, the driving force, then times the V. Remember, power is the rate of doing work, and work is force times distance, then over the time. So distance over the time is the speed. That's why we have the V here. Okay, then after that, what are we going to have here? The driving force is going to be equal to the power, which is 24,000 here, divided by the 32. So the driving force here is going to be equal to 24,000 divided by 32, that is 750 newtons. Okay, now using F, which is equal to MA, okay, you should know that this driving force is bigger than this one, let's say. So that is the net force here is going to be driving force minus the resistance force. Then this one is equal to 0 because acceleration is 0. So therefore, at steady speed or constant speed, the driving force will always be equal to the resistance force, okay, which is 750 newtons. Now, for power has changed. Remember, power is proportional to the driving force and the velocity. But since this is constant speed here, okay, I mean, the speed has been changed. That means we are going to get a new driving force. You see that? So for power, which is equal to 28,000 watts, okay, new driving force is going to be equal to this 28,000. Then we shall divide by that new speed, which is 36. So what do we get here? 28,000 divided by 36. That is 7,000 over 9. I'm just going to leave it exact over 9. Like that. Okay. Now again, using F, which is equal to MA. So that new driving force, which is 7,000 over 9, minus the resistance force, which is 720. The resistance is still the same. You see that? Then this one is equal to, the mass is 1,500, then times the acceleration. So don't you think now we can get our acceleration here? 7,000 over 9, then minus 750. Then we shall divide this one by 1,500. So what will be the acceleration here? 7,000 out of 9 minus 750. Then we divide by 1,500. So this is 1 over 54. I'm just going to keep it exact, 1 out of 54 meters per second squared. If you want, you can write it to 3 significant what? Figures. So that is that. Part B, it is given instead that the resistance to the motion of the car is this one here, 340 plus 4V newtons, when the speed of the car is V meters per second. When the engine is working at 20 kilowatts, the car is traveling at constant speed. That means acceleration is equal to what? 0. Okay. Now, again using our F, which is equal to MA. Okay. We shall have the driving force, new, or let me not write in new. Let me just write driving force is equal to the power, which is 20,000, then divide by the speed. Okay. So that driving force then minus the resistance then is equal to the MA. Okay. And of course, for constant speed here, then acceleration will be equal to 0. So the driving force therefore will be equal to R, because this one has gone to the what? To the 0. You see that? So the driving force is 20,000 out of V, yes, V, then is equal to the resistance force, which changed to this, that is 340, then plus 4V. We can cross multiply, that means this is 20,000, which is equal to 340 of V, then plus 4V squared. So bringing this one this way, we shall get a quadratic equation 4V squared, then plus 340 of V, then minus the 20,000, which is equal to 0. Then I can factorize out the 4. It is common, then plus 340 divided by 4, that is 85. So we have 85 of V, and then 20,000 divided by 4, of course, this one will give us a 5, then 1,000. So 5,000, which is equal to 0. When you divide all through by 4, that one disappears. So we have a simplified quadratic equation here. Now we can use our calculator to solve this. I'll come to my calculator and I press mod. Then I go to equation, which is option 5. Then quadratic is option 3. Coefficient of V squared is 1. Then coefficient of V is 85. And then coefficient of the constant part is negative 5,000. So this one will give us 40 and then negative 125. So I will write negative 125, and then this one is 40, but you have to show the examiner how you have solved this quadratic equation, because there is a mark for attempting to solve, right? Now, from here, just bring this one here to give us a factor from which the roots come. So that will be V plus 125. Do you realize that I first left space here so that I can cheat the examiner by writing backwards? Then bring this one back. You will have V minus 40, which is equal to 0. So since this is speed, which is a scalar quantity, okay, then we shall take the positive value. They didn't ask for velocity, so constant speed is therefore equal to 40 meters per second. As simple as that. Question 6. A particle P moves in a straight line starting from a point O at Question 6 is coming from kinematics, but here we are seeing variable acceleration because we are given an expression of V. So in this case, we don't use the other three equations of motion. V is equal to U plus AT, S is equal to UT plus a half AT squared, and V squared is equal to U squared plus 2AS. Okay, so here we are supposed to use differentiation and integration. So a particle P moves in a straight line starting from a point O. At t seconds after leaving O, the velocity V meters per second of P is given by V, which is equal to 15 minus 2t, then bracket squared. Part A, find the values of t when the velocity of P is 100 meters per second. I'll just get this 15 minus 2t. Then I equate it to 100. And 100 is a perfect square. That means inside here, we are having 2. Not so. I mean, we are having 10. So it can be 10 or negative 10 because when you square 10 and negative 10, you get 100. So when we take the square root on both sides, we shall have plus or minus 100. Okay? So 15 minus 2t then shall be plus or minus what? 10. Okay? Now, I'll use this one. 15 minus 2t is equal to the positive 10, and then 15 minus 2t is equal to the negative 10. So 15 here minus 10 then is equal to 2t. If you take this one here and then this one this side, we are making t the subject. So here t will be equal to, this is 5 over 2. As simple as that. And then here we shall have 15 then plus 10, which is equal to 2t. And then t here is going to be 25 over 2. Then part B, they are saying that show that there is a particular value of t for which the velocity and the acceleration of the particle are both equal to 0. Now, you know that acceleration is equal to the rate of change of velocity. So it will be dv dt. You see that? Now, if v is equal to 15 minus 2t squared, then acceleration is going to be, drop this power here. So 2 into 15 minus 2t, reduce the power by 1, so that will be 1. Then times, differentiate what is inside here, you get a negative 2. So meaning we shall get negative 4 into 15 minus 2t. You see? All right. Then from here, I can even simplify it. And I say, this one is going to give me negative 60. Not so? So negative 60, then plus 8t. Now, they say that when both are equal to 0, so if this acceleration is equal to 0, then I'll have negative 60 plus 8t is equal to 0. Take the 60 this side, it becomes a positive, so t is equal to that 60, then divide by 8. So this simplifies to by 4, 15 by 4, 2. So 15 over 2 is the same as 7.5. 7.5. Then they also said when both velocity and acceleration are equal to 0. So when velocity is equal to 0, what do we have? So our velocity is 15 minus 2t squared, which is equal to 0. Take the square root. Then this one will be equal to 0. And then 15 will be equal to 2t. And then t becomes also 15 over 2, which is equal to 7.5. So this is the value of time, which is 7.5 on both occasions when velocity is equal to 0 and acceleration is equal to 0. Now part C, find the displacement of P from O at the time that the velocity and the acceleration of the particle are both 0. Okay? Now, we know that velocity is equal to the rate of change of displacement. Not so? That means displacement is therefore going to be the integral of velocity. So, and here we shall have the integral from 0 to 7.5, because that is the value of t at which both velocity and acceleration are equal to 0. So here we shall have 15 minus 2t, then squared dt. We integrate, you remove the integral sign. So this will be 15 minus 2t, increase the power by 1, it becomes a 3, divide by that new power, but then times the derivative of what is inside here, which is a negative 2. Okay? And then here we have 7.5, then 0. what are we going to have here? So this one is going to be 1 over the 6, okay? And with a negative, so I'll take that one outside just like that. And then I will have 15 minus 2t, then cubed. And then I will put my limits, the 7.5, and then the 0. So substituting in here, 1 over 6, we have 15 minus 2, then times 7.5. This one will give us 15, so that will be a 0. Then minus, we shall have 15 here. By the way, this one will be cubed. 15, then minus 2 times 0, and then we cube it. So this one gives us a 0, okay? Then we shall have negative 1 over 6 into 0, then minus, this one is 15 cubed. So 15 cubed. So in other words, we are having, this is a negative times a negative, that's a positive. So 15 cubed out of 6. What is our answer here? 15 cubed, then divide by 6. The answer is 1125 over 2, which is the same as 562.5 meters. As simple as that. Question 7. These are connected particles. Two particles A and B of masses 6.5 kilograms and m kilograms, respectively, are connected by a light inextensible string that passes over a smooth pulley. The pulley is fixed at the top of a rough slope, which is at an angle of alpha to the horizontal ground, where tan alpha is equal to 5 over 12. A is on the rough slope and B hangs below the pulley. The coefficient of friction between the slope and A is 0.4. Then part A, given that the system is in equilibrium, find a set of possible values of m. Now, we need to look at the forces that are acting on these particles. So here we shall have the weight, which is mg, and then there is tension, okay? Here we shall have tension, and then there will be mg sine theta here. So mg, this is 6.5 g sine of alpha. Then there will be the normal reaction here, and this will be mg cosine of theta. So this is cosine of alpha. Then if they are saying two possible values of m, we are going to consider two scenarios where A can move upwards or can move downwards. Okay, now they say that the system is in equilibrium, so we don't know whether m is bigger than the 6.5. They have not told it to us. Okay, now if the system is in equilibrium, that means we consider a point where A is at a verge of moving downwards. Are we there? So if it is at a verge of moving downwards, that means the frictional force will be moving upwards. Are we there? Then we shall also consider when A is at a verge of moving upwards. That is if this one is far bigger than this. Okay? So in that case, the frictional force will be acting downwards. So we shall therefore consider the mu r. Okay? Mu r, because this is a rough plane. Mu r moving this way or this way. Okay, so what I'm saying here is the system can be yes, the system can be on the verge of moving downwards or upwards, depending on the value of m. Depending on the value of m. So when I say I'm referring to A when I say it is on the verge of moving up and down. Okay, so if m is greater than let's say 6.5 kilograms. Okay, then this B will move downwards. This one will be on the verge of moving upwards. Okay, so we shall say B will be on the verge of moving downwards. You see that? So when you look at B, using F, which is equal to MA, mg minus T, then will be equal to what? 0, because the system is in equilibrium, so acceleration is 0. So in other words, this implies that T is equal to mg, and you know g is taken to be 10, so this one will be equal to 10m. You see that? Now here B will be on the verge of moving downwards, then A will be on the verge of moving upwards. So let me just take this one here, and then I duplicate it. Then I write upwards here, the verge of moving upwards. Okay, now looking at A, we have the tension here. If A is on the verge of moving upwards, that means the frictional force will be acting downwards. So the only force that is moving upwards is the tension. So tension here then will be equal to mu r, then plus the 6.5 g sine alpha. Are we there? Okay, this one is 10m, remember? And then coefficient of friction is 0.4. Then r, you know, it is equal to this 6.5. There is no perpendicular movement to the plane. So times, it is 6.5 g, then cosine of alpha. So our r is 6.5 g, and then cosine of alpha. So we need to find cosine of alpha and then sine of alpha. Since we have tan alpha, which is equal to 5/12, okay, I can come here and then I get those values. So I have alpha here. Tan is opposite over adjacent. So meaning what we are having here is 5 squared plus 12 squared under the square root. 25 plus 144, that is 169. Root of 169 is a 13. So that means that sine of alpha, which is equal to the opposite over hypotenuse, then will be 5/13. And then cosine of alpha will be equal to the adjacent, which is 12, out of the hypotenuse, which is what? 13. Now, we shall come to this one here, and we say sine of alpha, cosine of alpha here, we have gotten it as 12 out of 13. Then plus, this is 6.5, g is 10, on this one here, then sine of alpha is 5/13. 5/13. Pardon me here. 5/13. Okay, now that means we can get the value of m. Okay, so m is going to be, now this one here will give us 65. Then 13 goes into 65 5 times. Are we there? Then 12 times 5, that one will give us 60. 60 times 0.4, that one will give us a 24. Okay, so that one gives us a 24. I'll have 10m, which is equal to 24 here. Then again, this is 65. 13 goes into 65 5 times. Then with that 5, so 5 times 5, we get 25. So meaning m is equal to, when I add these two, that is 49. Then I divide by the 10. So meaning m is going to be equal to 4.9. Okay, that is one value. Then I can also have m. I'm going to do the same thing here. If m is less than 6.5, then b will be on the verge of moving up, okay? Because this one is lighter, so this one will be taking it down. So b will be on the verge of moving upwards, and this one here downwards. Upwards, then downwards. Just like before, when we consider b, still t is equal to what? 10m. So I'm just going to look at this one here. So if v is on the verge, b is on the verge of moving upwards, then this one is on the verge of moving downwards. That means the frictional force is acting upwards. So the upward forces are going to be the tension and then the mu r. So I will say T plus mu r, okay, T plus mu r then is equal to 6.5 G sine of alpha, okay. Then again, I will say plus, and again here I will put equals. See that? What else? We have a plus here, and then equals. Equals. So meaning our m here, what is it going to be? 25 minus 24, which is a 1, then over 10. So m will be equal to 0.1 kilograms. That is another possible value of m. Part B, given instead that m is equal to 12 and the particles are released from rest with the string taut. Use an energy method to find the speed of the particles when each particle has moved 0.6 meters. You may assume that this occurs before A reaches the pulley or B reaches the ground. Now you can see here that m, which is 12, is bigger than the mass of A, which is 6.5. So this implies that this B will be moving down. That's why they are saying that A does not reach the pulley and B does not reach the what? The ground. Okay, so this is my new diagram which I'm going to have here. So let me draw everything here. You must have the art of drawing, remember. So we are having our A here, okay, and so in here we are having mu r. Because it is going up, so the frictional force will be acting downwards. And there is also mg, okay, sine alpha. You see that? Then here we need that alpha there. Then the pulley is here, so I'll put a string here, and then it will connect to this one down. Now I'm going to have positions in here. So let's say B has reached here. This is the new position, but the first position is here, okay. This one here is the new position. Let me even make it a little bit dotted. So there is tension in this string. There's also tension in that string there, okay. Now this one here, A, has also moved, let's say up to where? Up to here. So the distance in here is 0.6 meters. But they have moved. Even this one is 0.6 what? Meters here. Okay. Then from there, when B here. This is our B, okay? When B reaches this point here, first of all, at this point, it has potential energy. So I'm going to put potential energy initial because of this vertical. This is our, this one is going to be my point of what? Reference, okay? Now, this being my point of reference, so there is vertical height here. That means there is potential energy. And since the system is starting from rest, then there is no what? Kinetic energy here when B is starting. The same to A, it has no kinetic energy here. It also has no potential energy because there is no vertical height generated. Now, when it moves up here, okay, when it moves up there, we are now going to have an H. Okay, there is vertical height generated. So it reaches a point here, and what is going to happen, this is A, final position. This is A, initial. This is B, final position. And then this is, no. This is B, final position. This is B, initial position. Okay. Now, we are going to have sine of alpha is equal to the opposite out of the hypotenuse, which is 0.6. You see that? So meaning H will be equal to 0.6 sine of alpha. Now, when A reaches here, it is moving with a certain speed, so it has kinetic energy. Are we there? Then when it also reaches here, there is vertical height generated, so there is potential energy. You see that? So at this point here, we don't know the velocity. And also B, when it comes here, it is at a certain speed. The same system is moving at the same one. So the same speed with which B is moving is the same for A. You get it? Okay, then here we shall have kinetic energy because of this speed, and there is no potential energy because the distance here has been, the vertical height has been depleted. Okay? All right, now let's begin. Remember, we have work done by the driving force is, minus work done against resistance is equal to change in mechanical energy. That is the work energy principle. Work done by the driving force minus work done against resistance is equal to the change in mechanical energy. And I've already said that mechanical energy is the sum of kinetic energy and potential energy. Okay. Now, from here, work done by the driving force, since these particles are falling by themselves, okay, then that means we are not going to have what? Work done against the driving force. There is no that driving force. It is not this mg, okay, that is driving this one down. No, it is not that one. It has to be an applied force there, okay? So this one is going to be 0. Then minus work done against resistance. So we are seeing resistance. So you are supposed to get the resistance, then times. When you get the resistance, what do you multiply with? You are going to multiply with the distance traveled. So the distance here is 0.6. And mu r from here, when we check backwards here, our mu r is this one here, you remember, which actually gave us the what? The 24. So I'm just going to write 24, then times the 0.6, okay? Then this one is equal to change in mechanical energy. So we have to get final. So for final, I'll put here final. I'll have kinetic energy. Let me write kinetic energy plus potential energy. That is for A, okay? Final, then plus, this is final for B. So plus kinetic energy for B, okay? Final. Then minus initial, what do we have? So initial here for A, we don't have kinetic, neither do we have potential energy. But we shall have potential energy for for B initially, because for it is there is that vertical height. Now let's substitute. This one here, 24 times 0.6, that one is 14.4, so we have 14.4, it's a negative. Then this side, kinetic energy for A is a half times the mass is 6.5, then times the speed, we don't know it, okay? Then plus the potential energy is mgh, so the m is 6.5 times the g is 10, and then the h is this one here, which is 0.6. Then sine of alpha, we got it here as 5/13, okay? 5/13, you see? Then let's go to the kinetic energy of B. That one is going to be a half times the m, which is now 12, times the speed of B would still be squared, that V, and squared. Then we shall subtract potential energy for B, that is mgh, so that is 12, then times 10, then times the h here is 0.6. Now let us solve for V. So this is negative 14.4, and then this one here will give us 3.25, yes, 3.25, then plus the 6, isn't that 9.25? So we have 9.25 V squared, and then these two simplified, what do we get? First of all, this one is 65, 13 goes in here 5 times, okay? So we have 25 times 0.6, 25 times 0.6, then minus 120 into 0.6. Okay, so that's a negative 57, okay, minus 57. So take this on this side. This simply implies that V squared is going to be equal to 57, then minus the 14.4, then out of 9.25, okay, and then we shall take the square root. So therefore V is equal to the whole of this, square root of 57 minus 14.4, and then down here we have 9.25. That is 2.15 to 3 significant figures, 2.15 meters per second. That is to 3 significant figures. So that is that. So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next videos.